Good afternoon, everyone. My name is Himanshu Nagpal, and today we will discuss the topic of attenuation absorption from the optical communication. And if time permits, we will discuss about the scattering loss also. So, attenuation is the transmission loss of optical fiber, which is the most important factor in bringing about the wide acceptance in the telecommunication. So signal attenuation is generally expressed in the form of logarithmic unit of the decimal, or signal attenuation can also be expressed in the form of decibel, which is when calculated, that is in terms of the power. So decibel is generally used when we compare the two power levels, which is defined for particular optical wavelength as the ratio of the input optical power into the fiber to the output optical power P naught from the fiber. That means if I say this is an optical fiber cable and this is the input power to the optical fiber cable, and if I say this is the output power from the optical fiber cable, so ratio of the P out by P in, ratio of the P out by P in can be defined in terms of gain also. But as we say that it is attenuation means there is a loss of power from input and we will get the output power which is less than the input power. So the loss is generally defined as the P out divided by P in. P in divided by P out. But if I want to say that, if I want to calculate the attenuation in terms of decibel, if I can calculate attenuation in terms of decibel, then I'll just have to put the 10 log of P in divided by P out. Clear? So now if I say input power in terms of voltage and output power in terms of voltage, then we can say that 20 log of V in divided by V out. Clear? Now if I want to say that I have a input power in terms of decibel and output power in terms of also decibel, then attenuation can be is equal to P input decibel minus में P out in decibel. Clear? So as we know that there is number of mechanisms which are responsible for the signal attenuation within optical fiber cable. There are number of factors which are responsible for the loss in the optical fiber, that is loss in the terms of amplitude of the input signal, amplitude of output signal with respect to the input signal. These mechanisms, these factors are generally influenced by the material composition, preparation and purification of technique which are used for in manufacturing the optical fiber cable, and the waveguide structure, that is the optical fiber ka waveguide structure. So these are the factors which are responsible for the signal attenuation, that is material composition, preparation and purification technique, and the waveguide structure. So these further categorize into major areas, which includes the material absorption, that due to the absorption by the material, that is the material absorption, and material scattering, and these scattering can be maybe linear or non-linear. And another loss or another factor which contributes in the attenuation that is the curve and micro bending losses. This micro bending and another one is the macro bending. These are the losses which also results in the, due to which results a attenuation in the optical signal. Next factor is the mode coupling radiation losses. That is, mode coupling means the interaction between the two modes which are traveling in the optical fiber cable, and interaction between the two modes results in the loss of power from the one mode. And due to the leaky modes, some modes are non-propagating modes which are decayed while traveling inside the optical fiber, and that are also the losses, and these losses are due to the leaky modes. The power of the modes decays to zero, and the power absorbed in the cladding. So there are also some losses at the connector in the splices. So these are the external losses, you can say, that due to the connectors and the splices, which also decreases the value of the output signal with respect to the value of the input signal. So in optical fiber cable, the attenuation generally per unit length is usually expressed in the decimal per unit length, that is equal to 10 log of P input divided by P output. That is in terms of decimal, and this is equal to attenuation multiplied by total length of the optical fiber cable. So alpha is the signal attenuation per unit length, and when I multiply the signal attenuation per unit length multiply by L, will get the total attenuation of the optical fiber cable. So let's say this is the example which I have taken from the book on John M. Senior. That is the when mean optical fiber cable, when mean optical power is launched into a 8 km length of a fiber is 120 microwatt, means the optical power, that is P in, is equal to 120 microwatt, and the mean optical output power at the fiber output is equal to 3 microwatt, means P output is equal to 3 microwatt, and the length is equal to 8 km. So you can you'll determine the overall signal attenuation or loss in decibel through the fiber, assuming there are no connectors or losses. Now initially I assumed that the question is asking for the calculate the attenuation, and when there are no losses due to the connectors and the splices, that means I have to calculate the attenuation, and this from here you can calculate the attenuation, that is equal to alpha is equal to what? Alpha is equal to 10 log of P input divided by P out. This alpha is what? Is the total attenuation. Clear? So now just if I want to calculate the total signal attenuation per kilometer, that means if I calculate the attenuation from this factor and multiply by the total length of the optical fiber cable, that you will get the signal attenuation per kilometer. Clear? So the total signal attenuation is equal to 10 log of Pi by P out. As we say that the Pi is equal to 120 microwatt divided by 3 microwatt, that is you will get the total attenuation is equal to 16 dB. Now if I want to calculate the attenuation per unit length, so just divide the total attenuation divided by the total length of the optical fiber cable, that is equal to 2 dB per kilometer. Clear? Now the third part is I have to calculate the calculate the signal attenuation for a 10 km. Now the length of the optical fiber cable is 10 km, but we have the uses the splices at every 1 km interval, each giving attenuation of 1 dB. It means if I say that this is an optical fiber cable and this optical fiber cable has a length of 10 kilometer, and at every kilometer, at every 1 kilometer, there is a use of splice here. So for a duration of 10 kilometer, we will use the 9 splices, and each splice giving a attenuation of 1 dB. That means the total attenuation due to the overall splice, that is equal to 9 dB. So as we have already calculated from the second part, at this attenuation per kilometer is 2 dB, it means for 10 kilometer the attenuation will be 20 dB plus में 9 dB attenuation due to the splices. That means the total attenuation, that is equal to, will be what, 29 dB. Now fourth part is to calculate the numerical value of the input output power ratio. Means I'll have to calculate the input output power ratio, that is P in divided by P out. As we know that it will be equal to what, 29 dB. No, it is 10 log of P in by P out is equal to 29 dB. So I have to calculate the P in by P out. So that will be equal to 10 की power में 2.9 dB. That is equal to P in by P out. That is equal to 10 की 2.9. That is equal to, that is the numerical value of the P in by P out. Now the next topic is the material absorption. This is the one of the mechanism in the loss or in the signal attenuation. It is the material absorption loss. So there are two categories in which we will discuss the absorption losses, and then the absorption losses we will first discuss about the loss due to the material and due to the material absorption. Now as we know that the material absorption is the loss mechanism which is related to what, which is related to the material composition and the fabrication process used in the, and the fabrication process used for the fiber, which results in the dissipation of the sum of the optical transmitted optical power as heat in the waveguide. Clear? So this absorption, this material absorption is due to the material composition and the fabrication process used in the making of the optical fiber cable. But this material, this absorption is maybe intrinsic or extrinsic. And what is this intrinsic? This intrinsic absorption is generally caused by the interaction with one or more major components of the glass. Means the glass from which it is made up of, the interaction between the molecules or different components of the glass, that is the intrinsic absorption. Clear? And another loss, that is the extrinsic loss, extrinsic absorption loss, and this is caused by the impurities within a glass. When there is an impurity in the within a glass, the molecules in the used in the fabrication of the optical fiber cable, these impurities, this material have some impurities, and these impurities caused in the reduction of output signal. When there is a reduction in the output signal or output power, it means there is a loss. And when there is a loss, that is will be there is a attenuation, and this attenuation is generally due to what? Due to the absorption of the signal, and this signal is absorbed by the impurity, that is known as the material absorption, and material absorption, it is the extrinsic absorption. So intrinsic absorption is what? Intrinsic absorption. Now we'll elaborate what is the intrinsic absorption. Intrinsic absorption is an absolute pure silicate material glass. As we know that the optical fiber is made up of what? Pure silicate glass, but it also has some little type of intrinsic absorption due to its basic material structure in the near infrared region. Means as we know that the optical fiber is made of pure silica glass, and pure silica glass has some basic material structure which is providing a absorption in the near infrared region. So it does have two major intrinsic absorption mechanism at a wavelength of from 0.8 to 1.7 micrometer, which leave a low intrinsic absorption. Means in the optical power window there is a less intrinsic absorption, which is in the range of 0.8 to 1.7 micrometer. But when I've said that there is a low value of intrinsic absorption, but there is some value of absorption and due to the intrinsic material of the property, but there is some absorption. But now see that there is a fundamental absorption edge, the peak of which are centered in the ultraviolet region. This is due to what? Due to the simulation of electron transition by the within a glass. Means when the optical fiber is operated in the ultraviolet region, it means at that time the electrons, there is a molecules of the material in the material absorption, and the molecules in the glass, which have some electrons. There is an electron transition within a glass by higher energy excitation. The effect of these both processes can be minimized by the suitable choice of by both of core and cladding. Means this material absorption will always be there, but this can be minimized by the suitable choice of material which is used in the manufacturing of the core and the cladding. For example, if I use the non-excite glasses in which fluorides and chlorides have infrared absorption at a longer wavelength, clear, but at the far infrared region giving a less absorption to the longer wavelength transmission compared to the oxide glasses, clear. It means at longer wavelength it provides a less attenuation non-oxide material as compared with the oxide glasses. So now this is the graph which I have taken from the John M. Senior, that is graph of the attenuation with respect to the electron energy and also with respect to the wavelength. Now see that if I increases the wavelength of the signal, the ultraviolet absorption is decreases to certain point to the 1.3 micrometer, but at around 1.3 micrometer or 1.4 micrometer the infrared absorption starts increases, clear. And this one is the total loss. This is a total graph of the total loss with respect to the wavelength, and this total loss consists of both absorption and the scattering. Now next is the extrinsic absorption. Now extrinsic absorption, in the practical we have discovered that the optical fibers are prepared by what? Pure silica glass. But these fibers, initially these fibers are what? Are made up of some conventional fabrication techniques, and due to the normal in the earlier phase we are using the conventional fabrication techniques, that is the conventional melting techniques, in which the major source of signal attenuation is the extrinsic absorption from the transition metal element impurities. Due to the transition metal, these transition metals are act as a what? As an impurity to the in the fabrication of the in the fabrication of the optical fiber cable, and these transition metal causes the absorption. So some of the major or more metallic components in the optical fiber cable we'll discuss in the next slide. So these impurities are generally what? Copper, chromium, which causes attenuation of what? 1 dB per kilometer in the near infrared region. But this transition element contamination can be reduced to a very low level, that is 1 part per million, that is 1 part in 10 to 10, by glass refining technique, or you can say by improving the fabrication techniques, by using the latest fabrication technique, that is vapor phase oxidation, which is largely used, eliminates the effect of this metallic impurities. Clear? Another major impurities extrinsic loss is due to the hydroxyl ion or the water vapors which are dissolved in the glass during the fabrication process. So this is a graph which I have taken from this is the table which I have taken from the John M. Senior book, and in which you will see that the chromium 3+ ion, that is act as an impurity, will have a peak wavelength of, will give attenuation of higher 1 dB at the peak wavelength of 625 nanometer. And similarly, you can see that the copper gives a higher attenuation at 850 nanometer wavelength. So these are the materials or transition metals which providing a extrinsic absorption at these peak wavelength. Now this graph shows, also taken from the John M. Senior book, in which we will see that the attenuation with respect in the graph between the attenuation and the wavelength, and you will see here that the attenuation is generally increases at these point, and this attenuation is generally higher at this point, that is around 1400 nanometer, that is the first attenuation, first overtone, and second overtone is the where the attenuation is higher at the around 900 or around, and this around 990 around, and this third overtone that is having a attenuation, very less attenuation at this around 700 nanometer. But this attenuation is mainly due to the what? The graph is for the hydroxyl ion group in the silica, which is dissolved in during the manufacturing of the optical fiber cable. Clear? Now next one shows the measured attenuation. The graph between the attenuation and the wavelength. Clear? Now you will see here that the, as we know that the ultraviolet attenuation absorption is decreases, while the infrared absorption increases at the higher wavelength. And this is the graph of the scattering, we will discuss in the next coming topics. And this is the constant absorption due to the waveguide imperfection. This is this does not depend on the wavelength. This is having constant absorption due to the waveguide. So overall, experimental graph between the attenuation with respect to the wavelength, that is around 1400 nanometer. Around 1400 nanometer, the absorption suddenly gets increases, and the attenuation around 1550 nanometer, having a least attenuation or absorption, you can say, at this 1550 nanometer. Now we will here discuss the scattering loss. Scattering loss is what? Scattering loss is generally when the light get scattered in the optical fiber cable, and this scattering of the light causes the loss in the signal. So scattering loss is what? Is loss in glass arise from the microscopic variations in the material density, from the compositional fluctuations, and from the structural inhomogeneities or the defects occur during the fiber manufacturing or the fiber fabrication. So scattering losses generally arises due to the, let's say if I say this is the optical fiber cable, and this optical fiber cable has some defect in the optical fiber cable during the manufacturing. When a light incident on this defect or on this particle, the light gets scattered. The light may get scattered in this direction, in the forward direction. Some light gets scattered in the backward direction. So this one is the scattering, and this scattering causes the loss of the input signal. So this scattering is generally categorized into two parts, that is linear scattering and the non-linear scattering. So this linear scattering is further divided into two types, that is the railing scattering and the mice scattering, and the non-linear scattering is further divided into stimulated Boolean scattering and the Raman scattering, that is the SRS and your SPS. So now what is this linear scattering? Linear scattering is the mechanism, is the cause of the transfer of some or all of the optical fiber cable, optical power from one mode to the another mode, and this power transfer from one mode to the another mode is transferred linearly. Clear? So this type of scattering is known as the linear scattering. So this process, which this scattering results in the attenuation of the transmitted light, which does not continue to propagate within a fiber core but is radiated from the fiber core. Means this loss results in this loss of signal results in the output power value goes to low, and this transfer of power from one mode to another mode, this transfer of power may be transferred to the leaky mode, and this leaky mode, which will not continue to propagate within an optical fiber cable and is radiated from the fiber core. That means this power is lost from the optical fiber cable because that power is transferred to the leaky mode, and this leaky mode will not travel inside the optical fiber cable. So linear process or linear scattering does not change the change of frequency in the scattering. Means after scattering, if I say this is a light, and this after scattering, the signal, the frequency of this signal or scattered signal will not change. So this linear scattering is categorized into two types, that is the railing and mice scattering. So railing scattering is the dominant intrinsic loss mechanism in the low absorption window between the ultraviolet and the absorption, infrared absorption, and it results from the what? This railing scattering results from the what? Inhomogeneity of the random nature occurring on a small scale compared with the wavelength of the light. It means what? So when the material or the particle size is very small compared to the wavelength of the light, this type of scattering is known as the railing scattering. When this material size is very less than the wavelength of the signal or wavelength of the light, then this particle will cause what? Railing scattering. Clear? This railing scattering results in the refractive index fluctuations, and which arise from the density and the composition variation, because when some particle is present inside the optical fiber cable, this impurity or this inhomogeneity which cause the fluctuation in the refractive index material and the compositional variation. This compositional variation can be improved by the improved fabrication techniques. So this is a railing scattering when the particle size is very smaller than the wavelength of the material, that is a railing scattering. And this is railing scattering coefficient, that is how much scattering is there, that is given by the gamma r equal to 8 pi ki power 3 divided by 3 lambda into n power 8 p square beta c k into tf, and this gamma r is the Rayleigh scattering coefficient, and lambda is the wavelength of the optical signal, n is the refractive index of the optical fiber cable, that is medium, or you can say core, p is the photoelastic coefficient, and beta is the isothermal compressibility at the effective temperature. So next one is the Mie scattering, in which the inhomogeneity size is comparable to the wavelength, and this result from what? Non-perfect cylindrical structure of the waveguide. This is caused by what? Fiber imperfections, core cladding refractive index, and diameter fluctuations, and the strain and the bubbles which are produced in the this one, in which you will see that the scattering, the inhomogeneity size is greater than the lambda by 10, results in the Mie scattering. So these are the losses which we have discussed. That is the absorption loss, and after absorption we have discussed about the scattering, that is the linear and the non-linear. Only the linear scattering we have discussed. So the book I have referred, that is the John M. Senior Optical Fiber Communication Principle Practice, and the author of this book is the John M. Senior, from the Pearson Education publication. Thank you.